So to start, radical expression. So the big thing to remember is that radicals and exponents are inverses of each other, just like multiplication, division, addition, subtraction. A lot of finding roots you can do with a calculator, but it's important to be able to recognize a lot of our most common roots. Okay, perfect squares up to 144, and perfect cubes up to 125. Being able to recognize some of those as you see them over and over is going to become really helpful as we move into simplifying our radical expressions. But when we look at a radical, the square root of 36, we know it equals 6 because its inverse is 6 squared equals 36. That's that relationship between exponents and radicals. Okay? And we can extend that to any exponent. So these numbers will always match. Now, on 36, there's no number there. What can I assume the square root of 36 is? Here. 2. Okay? Because it's a square root, right? The inverse of square root. When we move into third root, fourth root, fifth root, then we're going to have those numbers there. If there's no number listed, we just assume that it is a 2, and we're never going to have a 1. Okay? There's no first root, because the first root doesn't do anything. Okay? So just some vocab. That number in the front we call the index. So when I'm talking about the index, that's the number I'm referring to. The index is going to correspond with the exponent when you're doing that inverse relationship. Okay? So the inverse of square rooting is squaring. The inverse of cube rooting is third power. The inverse of fourth rooting is fourth power. We've got our radical sign, and then the inside part is called the radicand. Whether it's a number or an expression, it's called the radicand. The whole thing together is a radical. So again, a lot of these are just common roots that you should be familiar with. Again, the calculator can do a lot of the heavy lifting for these. If you're just stuck and you want to just get the answer. But again, looking at the relationship between the roots on the left and the exponents on the right and that inverse relation equivalency there. Notice again that so the cube root of 27 is 3 because 3 cubed is 27. The third root, or the cube root of 216 is 6 because 6 to the third power is 216. Fourth root, 4 to the fourth power. Fifth root, 3 to the fifth power. See that relationship. Okay? Same thing with our fractions and our decimals. Okay? Having that relationship. What number times itself 4 times gives me 16 over 81? Well, it's 2/3. To the fourth power. 2/3 times 2/3 times 2/3 times 2/3 will give me 16 over 81. And the same thing with decimals. What times itself 3 times gives me 0.6064. Well, it's 0.4 times 0.4 times 0.4. Okay? That back and forth relationship. Now, when we're dealing with roots, we have principal and negative roots. When we're given the square root of 36, we're given the square root of 36 that equals 6 because 6 squared equals 36. There's a different number that I can square and still get 36. Which one is it? What number can I square and get 36 other than 6? Square and still get 36. Negative 6. Negative 6 squared also equals 36. So we have to have that distinction of, well, do I want positive 6 or do I want negative 6? That's the difference between principal root and negative root. If there's no sign in front, it wants the principal root. If there's a negative in front, it wants the negative root. So it'll tell you which one to get, or the negative root. Okay? That's only if n is even. Okay, and then again, a has to be positive or 0, otherwise we can't take the root. So if n is even, we've got principal root, we've got negative root. If our index is even, but our radicand is negative, it is not a real number. When we get into complex numbers, then we'll simplify using complex numbers, but until then, it's just not a real number. Okay, it'll always be not a real number. It's just how much are we going to do with that information will vary as we move in. But again, even index, negative radicand, not a real number. If our index is odd, then we don't have to worry about positive and negative. We're just going to match whatever fits. Okay, so if my radicand is negative, then my answer is going to be negative. If my radicand is positive, then my answer is going to be positive. Okay, I don't have to worry about positive and negative root because there's only going to be one solution if our index is odd. All right, so just kind of looking through these. So the square root of 36, 6. Okay, how do I know it wants positive and not negative root? There's no sign in front, so it wants positive. Okay, but for B, what do I want? Negative 6. Okay, because it gives me the negative, so it wants the negative root. Okay, 4th root is 16. 2. Okay, and it wants positive 2 because there's no sign in front. Negative 4th root of 16. Negative 2. Negative root, so it wants the negative root. 4th root of negative 16. Not real. Okay, we'll get to complex numbers when we get there, but right now we're just going to say not real because it's an even index and a negative radicand. Even index, negative radicand, not real. Okay? 5th root of 243. 3. 3 times 3 times 3 times 3 times 3. 5th root of negative 243. Oh, it's real because that's not even. Negative 3. Even index, negative radicand, not real. Odd index, right.
In the index is the number that's outside of the thing?
Outside.
Oh,
The little tiny. Slide number. Slide number 7? Yeah. Okay. Give me, so here I've got negative square root of 16, right? Okay? Because the negative's on the outside. So in order to get a 4th root of 16 is 2 times 2 times 2 times 2, right? So if I have negative 2 times negative 2 times negative 2 times negative 2, that equals a positive 16. If I have 2 times 2 times 2 times 2, it equals a positive 16. There's no number I can raise to the 4th power and get a negative 16. So it's not real. Alright? These won't show up a ton, and there's a little typo on your sheet on the next slide, so I'm going to have you fix it. But it's important to kind of note that this will happen, we end up with absolute value. When your index and your exponent, if you have an exponent inside your radicand, if they match, then what we do is we end up taking the absolute value. Because think of it this way. If I have a number, negative 2 squared, okay? If I have negative 2 squared and then I have the square root of it, if I go through my order of operations, negative 2 squared is 4, right? And then the square root of 4 is 2, all right? But we also know that these are inverses, and inverses undo each other. And so a lot of times what we want to do is we want to skip this whole process and just cancel. But the problem is my answer is not negative 2. So if we do that elimination, we have to put it in absolute value and then continue to simplify if we can. All right? So when that index and the exponent match, and we do some simplification, some canceling of the inverse operation, we have to put our radicand in absolute values and then simplify it as we keep going. Because it has to end up being positive. Whenever I square something, it becomes positive, if it wasn't already. And then I can square root it, and it's still going to be positive. So we need to make sure that that sign is preserved moving through. Okay? So this one was different on your worksheet. I want you to change where the parentheses are. Okay, I want you to change where the parentheses. So again, we're looking at the square root of 15 squared. I cancel those out, but I go ahead and place it in absolute value. Okay? Because I need to make sure that this stays positive, which again, it's not going to make a big difference here. But once we get into negative values and variables, that absolute value is really important to preserve that positive nature of that radicand. So I have negative 12 squared. If I want to cancel those out, I need to put it in absolute values and then simplify. When I'm at a variable, again, I can cancel it out, put it in absolute value, but it needs to stay. Okay? It needs to stay there in that absolute value because I don't know what y is yet. I can't take it out and just say that it's y, because what if I later decide that y is negative 3? Well, then my answer would be -3, but it's not. It has to be a positive value. So if I said that y equals -3 and I substitute in, I still need to make sure that I end up with a positive value. So if you have a variable in absolute value, it needs to stay in the absolute value. Okay? And then here, again, same kind of idea, but I have a negative here. So again, I square it. It's going to become positive. Okay? And so we need to make sure that we put it in the absolute value, and then again, leave it simplified in the absolute value. So again, that extends as, again, these match. Okay? But notice about all of these indexes and these roots, or sorry, exponents, they're even. This same rule does not apply if they're odd. If it's odd, then it's just free for all. Okay? Just simplify it. All right. But if it's even, we have to preserve that absolute value. Okay? You use absolute value when your index is even. You don't have to do it when n is odd. All right. So, A, am I going to need absolute values? Yep. So that cancels the absolute value of -5, which is 5. B, do I need absolute value? Is that even? Okay. That's odd, so I don't need absolute value, so it's just -5. Okay. Odd, no absolute value. Even, yes, absolute value. Do I need absolute value? Yep. Cancel those out. So I have my first negative, then I have the absolute value of -3. Absolute value of -3 is 3, and then just bring that front negative to follow. Okay? Here. These don't match, but I can break up m to the 8th, and I can write it as 4th root of m squared to the 4th. That's our power rule. Okay? We break apart the factors of our exponents. 2 times 4 gives me the 8, so I have 2, so m to the 2nd power to the 4th power. So now they match. Do I need to use absolute values? They're even, right? So even says yes, let's use absolute value. So I have negative, that cancels, absolute value of m squared. Okay? Now, keep this in mind. When I square something, that number always becomes what? Positive. When I do the absolute value, that number always becomes what? Positive. So that positive nature is redundant with that question. No matter what value I plug in for m, the square is going to make it positive. So I actually don't need to keep the absolute value because it literally will make no difference. Negative m squared. Whatever I plug in for m is going to become positive. Whether I have the absolute value there or not, it's not going to make a difference, and then it's just going to be negative at the end. Okay? So it's seeing, does that absolute value make a difference in the final answer or not, or is it redundant? All right, now, this is the fun stuff. This is the nitty-gritty. So all of that is leading up to this. This is our most important stuff, is simplifying radical expressions. We're going to be focusing on product and quotient rules. Product rule says that if we're multiplying two radicals and they have the same index, this is really important. They have the same index. You can combine them over one or under one radical. Okay? Two radicands, same index, being multiplied, you can combine them under the same radical symbol. Okay? You can also go backwards if you want to split it apart. That's how we're going to simplify a little bit later on, is we're going to split it apart. So the product of two nth roots is the nth root of the product. So I look at A, I check. Are my indexes the same? Yes, so then I can multiply them together. So this combines to be the third root of 2 times 7, which is just 14. If you get a radicand that can be simplified together, go for it. But I can't simplify the third root of 14 at all, so it just stays as third root of 14. That is it, multiplied together. B, do I have the same index? Yeah, so I can combine it as 6th root. 8 times 2 is what? 16. And then r squared times r to the third, r to the fifth. Same index? Yep, so combine it. 5th root. 9 times 8. X times x. Y squared times y squared. Same index? No. What's the index on square root of 7? 2. Okay? So the index is not the same. So I cannot simplify, so it is already simplified. Easy. Quotient rule on the next slide is going to be the same idea. Okay? If it's division, we can either separate it as 2 radicals, or we could take 2 radicals being divided and combine them into 1. Depending on the situation, we'll determine which one's going to be more useful. Okay? So, division, 2 radicals, or 1 radical under the same fraction bar. So you can write it either way. It makes the fractions a little bit easier. Sometimes allows us to simplify when part of our fraction isn't a perfect square. Or makes it easier just to identify that we can simplify it at all. Instead of thinking about what fraction times itself gives me 100 over 81, we can write it as the square root of 100 over the square root of 81 and do both of those square roots. 10 over 9. Okay? When we look at B, we write it as 2. Okay? The square root of 11 over the square root of 25. 11 is not a perfect square, so I can't simplify it and get a rational number. So that stays the same. But I can square root 25. 5. So it allows us to simplify when our fraction as a whole isn't a perfect square, but the numerator and or denominator individually can be simplified. So cube root of 18, there's nothing I can do to simplify that, but I can take the cube root of 125. 5. Then I've got the square root of y to the 8th over the square root of 16. What's the square root of y to the 8th? Y to the 4th. Divide by your index. And over 4. Negative cube root of x squared. So my exponent is smaller than my radicand, or my index. Exponent is smaller than my index, so I can't simplify that. But if I have the third root of r to the 12th, the exponent is larger than the index, so I can simplify that. The third root of x squared over r to the 4th. 12 divided by 3 gives me 4. The third root of r to the 12th, you divide your exponent by your index. 12 divided by 3 gives me 4. Indeed. Right. Good try. Almost done. Any questions on this? Good. All right. So product and quotient rule. So what we do is we combine those and use them in order to simplify radicals that aren't necessarily perfect squares. Okay? So what constitutes a completely simplified radical? 1, no fractions inside the radical. No fractions. 2, no radicals in denominators of fractions. Okay? No fractions in the radicand, and no radicals in denominators. Outside of that, the radicand has no factors raised to a power greater than or equal. We've looked at all the factors inside our radicand and figured out which ones are perfect squares or cubes or fourth power, whatever. Simplified those and left everything else inside. And then again, the exponents can't be simplified because they don't have a common factor other than 1. Okay? So, none of those are perfect squares or perfect cubes or fourth power. Okay? So we need to make sure that we can find factors of our radicand that are perfect squares or perfect cubes that can be rooted with the index that we have. So when I look at 32, what is a factor of 32 that is a perfect square? 4. Do I have a bigger one? 16. If you can find the biggest one, go with that. Okay? But I'll show it both ways so that in case you get stuck, you can find it. So I can do the square root of 16 times 2, which I can split as the square root of 16 times the square root of 2, which allows me to then square root the 16 and leave the 2 inside the radical. Okay? If you can't find the biggest one, And you say, okay, I want to know forced factors, so let me start with that. Okay? So I've got the square root of 4 times 8. And then you look at 8 and say, oh, well, 8 also has a perfect square factor. So I can write it as the square root of 4 times 2. Okay? You can either combine those into 16, and you end up here, or you can take each of those roots individually and multiply them together at the end. Either way is fine. If you can find the biggest factor that's rootable, then it's going to be faster. But if not, we'll just have a couple extra steps to get there. Okay? But make sure that you simplify it completely. Don't stop at 2 square root of 8, because 8 has a rootable factor. So it needs to be as well. Largest factor of 300, that is a perfect square.
300.
So I've got 100 times 3. This gives me a square root of 100 times the square root of 3, 10 root 3. All right. What are my factors of 35? 5 and 7. Are either of those perfect squares? No. So that can't be simplified any further. Already simplified. There's no factors of 35 that are perfect squares, so there's nothing I can do with it. All right. When we get to third power, that's when knowing some of those common cubes is helpful. 8, 27, 64, 125. So you can look at that number and ask yourself, are any of those factors of 54? Is 8 a factor of 54? No. Is 27 a factor of 54? Yeah. The third root of 27 times 2. Third root of 27 times third root of 2. What's the third root of 27? 3. 3, third root of 2. Please make sure it is clear what number is your index and what number is the factor on the outside. Okay? Gotta be real quick. Alright, so make sure that index is.
Wait, can you name the thing?
27, 64, and 125. That's 2, 3, 4, 5.
And this is just, if we were to answer it and we would forget, we do all the work with the cube root.
On MathLab, absolutely. On a test, it'll be a little bit off. Not major. Okay? I don't want to spend time on the fourth root because that's going to take a while, but the concept's the same. Okay? I want to make sure that we get into these. So, square roots, all right? Assume that all variables represent positive real numbers. That's just taking care of the fact that if I square root z to the 6th, I don't have to worry about, okay, or z, or x to the 5th, I don't have to worry about what if it was negative, okay? Well, then I'd have to square root negative and it becomes an issue. So this just says, hey, we can simplify everything. There's no restrictions, all right? So I've got coefficients and variables. I can still take the square root of 25, okay? But I can't take the square root of p to the 7th. So what's the largest factor of p to the 7th that I can take the square root of? P to the 6th. So split it apart into p to the 6th and then just p. Because p to the 6th times p is p to the 7th. 6 can be divided by my index of 2, and then 1 is just what's left over. So what's the square root of 25? 5. What's the square root of p to the 6th? P to the 3rd. And then I just have that lonely variable inside my radical. 25, square root of p to the 6th, and then I can't square root p, so it stays. What's your question? 6 divided by 2.
It's divided.
Your exponents are divided by your index. Your exponents are divided by your index. Alright? 72 a perfect square? So what's the largest factor that is?
9,
Bigger, not a perfect square.
36.
So I've got 36 and 2. Is y to the third a perfect square? Split it into what? Y squared and y. X, well, can't do anything with that. So focus on what's your perfect squares. 36, what's the square root of 36? 6. Okay. Y squared, what's the square root of y squared? Now, I'm done with those. 2y and x can't be square rooted, so I just keep them inside the radical. What's 36 times 2?
Oh, yeah.
72 was factored for 36 and 2. Now we're looking at our third root. Negative 27. Can that be cube rooted? Yeah, because it's 3. Okay, so that's a perfect cube, so that's good. All right, y to the 7th. Nope, so what do I need to split it in? 6 and 1. So y to the 6th. Y. X to the 5th. Can 4 be divided by 3? 2. X to the 3rd and x squared. Remember, I want third root, so I'm looking for multiples of 3. Z to the 6th. Z to the 6 is good. All right. All right. So negative 27. Cube root of negative 27. 3. Cube root of y to the 6th. Y squared. Skipping that one. X to the 3rd. X. Y. That. Skipping that. Z to the 6th. Z. And then what's left? What's left on the inside? Okay. I'm just going to put the x squared first because alphabetical. Doesn't make that much of a difference. All right, factor of 32 that has a fourth root. 8 has a third root, not a fourth root. You can also do a factor tree. Let me take a second to do a factor tree. Okay. Get your prime factors. And since we're dealing with fourth root, I want 4 common factors. Okay, so 2 times 2 times 2 times 2, that's 2 to the 4th times 2. If I want the fourth root, I just take the fourth root of 2 to the 4th, and I leave the 2, giving me 2 root 2. Okay, that's what we're going to do here. So 16 is my factor. Negative 16 times 2, a to the 5th, a to the 4th, and a. So a to the 4th and a. B to the 7th, the 4th, and b to the 3rd. Good. Okay. So what's the 4th root of 16? 2. Leave the 2, 4th root of a to the 4th, a, 4th root of b to the 4th, b, good. So everything else, the 2, the a, and the b to the 3rd will stay, and because it's negative, make it negative. Oh, yes. I need there and there. Yeah.
That's how you write that, right?
Yeah. Put a little 4 there. Thank you.
You have
Yep. Otherwise, it's a square root, not a fourth root.
We do that with the third.
If it's a fourth root, if it's a third root, if it's an eighth root. Yep. You gotta write the index.
So did you write the thing right there?
Yeah, I forgot it there too. It's easy to forget. I will fully admit that, but it's gotta be there.
Are you gonna count it wrong like this?
Yes. Any other questions?